much thank you to the Stockholm Environment Institute, who is the main inventor and host of this excellent tool, the Long Range Energy Alternatives Planning System, with now an integrated benefits calculator. We'll hear more what it actually means. But we have Charlie Heaps, the lead LEAP developer from SEI in Boston, online, and he will speak to us. We have Johan Kuylenstierna, I'm very sorry for my poor Swedish pronunciation, the policy director of the SEI sitting in New York. And of course, we have in person Chris Malley from SEI as well here from York. Mm-hmm. And you will show us a little bit live demonstration. I'm not going to talk anything more because I think you had in the invitation a few words about LEAP already, and I think it speaks for itself. I just want to say that for the last 4 years, this is a very old tool, and Charlie will tell you about it. But over the last 4 years, we, as Climate and Clean Air Coalition, has supported the development of a new or an expanded integrated benefits calculators to also be able to do different mitigation scenarios nation scale wide to estimate avoided mortality, crop losses, and more on climate benefits. It's basically a planning tool we are talking about here. And it includes, it's in an integrated way, both air and climate pollutant emissions, including short-lived climate pollutants, of course, which is our particular interest. But the most important point is that it's an integrated tool. So with no further delay, I think it's better to hear our colleagues speak from SEI. We can talk to you more about the National Action Planning Initiative that we have in CCAC, and Elsa is the coordinator for that initiative, but that is something we can also do more of, I think, together with some of you who have worked in those countries. We work in more than 16 countries, and it will become 21 countries, I believe, over the next year. So it's quite widespread as well in terms of institutional strengthening and planning support. So over to Elsa and then over to SEI.
Hello, everyone. So I'm Elsa and I coordinate the SNAP initiative in the CCAC, so National Planning Initiative. I turn over now to Charlie Heaps, not Leap, based in Boston, who got up very early for us this morning. Over to you, Charlie. You should be able to share your screen. Yes, we can see your screen.
Can you see it now?
Yes.
I'm just going to make it full screen. Is that working?
Yes.
Okay, thanks, Elsa. I understand I've got about 15 minutes. Is that right, Elsa?
That's correct.
Okay, so what I'd like... good morning, good afternoon, wherever you are in the world. My name's Charlie. I'm the main developer of LEAP, and in the last few years been working with the team in New York and folks at US EPA and UNEP and CCAC to develop this extension to LEAP called the Integrated Benefits Calculator. Chris and Johan are going to go into some depth about the Integrated Benefits Calculator. I'll mention it in passing, but I'm just going to spend the first 15 minutes giving you a quick introduction to what the basic sort of LEAP package looks like, and then Chris and Johan will tell you more about the extensions that we've been working on the last few years. So what is LEAP? So LEAP is it's a Windows-based integrated energy and climate mitigation modeling tool. The general idea of LEAP is to be a tool that's useful to developing country climate and energy practitioners. As Helena mentioned, it's really sort of the main focus is that it's an integrated tool. So it's not just for looking at one sector, it's for doing plans for a country as a whole. It starts at the point where sort of the inventory process ends. So the inventory process is looking at what are your current emissions, but LEAP's thinking about mitigation. It's thinking about what different pathways might be followed in the future. So you might think about your, where emissions are headed today under baseline scenarios, but you can also think about the implications of policies. It has been very widely used now. We have users in basically every country, and we've been working on it, as Helena said, since since before I care to remember, but there's at least sort of 30 years of development have gone into the tool. Most people using the tool trees have been using it for their national communications and their communications to the UNFCCC process. But it's also increasingly being applied at subnational scales, at cities, and in states. In the US, it's very widely used, and in China, it's very widely used at the city scale. It's designed not as a sort of a geeky modeling tool. It's not designed necessarily for people who are full-time modelers. We've really put a lot of effort in to make it flexible, transparent, easy to use. It's not just about modeling, it's also about supporting people's data management needs, and about visualizing results and communicating results to stakeholders. So it's a tool where we try to have the tool talk to people in the language that energy and climate practitioners, decision makers understand. So it's not talking in a sort of in the way that modelers understand necessarily, although of course they can use it, but it's really focused on the needs of decision makers and practitioners. By design, it's very, as I said, it's very user friendly, and you can get started with it with fairly low levels of data. So it's very suitable in situations where data availability is poor or where institutional expertise is limited. So because of that, it's been very widely applied in developing country situations where maybe people don't have access to a lot of high quality data. But it's also fairly flexible. You can start out fairly simple with it. It has choices of methods built into it. So you can start out with something fairly simple, but then you can sort of build your model iteratively and get more sophisticated as you go on. Just a couple of geeky things. It does also include what's called an API, an application programming interface. So that means it's very good at talking to other models and other tools. And just a couple of examples of that. We've been using it recently to link to its sister tool, which is called WEEP, which is a integrated water resource planning model. And the API allows LEAP and WEEP to communicate to each other so that you can look at energy and water modeling issues and how they're linked to each other. So this is this so-called new branch of analysis called energy water nexus studies. You can also use it to link to other modeling tools, and in fact that's part of the way that we've been linking LEAP to this new integrated benefits calculator tool. So IBC is this new tool that examines health, agriculture and climate implications of scenarios. That's the work we've been doing, supported by CCAC, that Chris and Johan will be telling you more about in a minute. Just a few words on how LEAP is applied for mitigation analysis. So as I said, it does have very low initial data requirements, and that makes it usable in situations where good data is in short supply or expertise is limited, which is a very common situation in many smaller, poorer developing countries. The user-friendly design makes it very broadly accessible. So many of the tools out there are really only accessible to very expert users, and we've tried to make a tool that is much more accessible to a much broader community. It has a very demand-driven, end-use oriented structure, which is very good because it sort of frames the problem in terms of development goals and aspirations. So it allows people to look at what they can do in terms of climate mitigation, but also think about what the development implications are of those of their policy needs. It's also has very fast interactive calculations, so that helps encourage people to take a kind of an iterative approach to model building. So it's been a very common story in the past that people have tended to build mega models, and those projects have been prone to failure because it's too difficult to actually get the model working. With LEAP, you can build something simple and then you can refine it and gradually improve it over time. Okay, just want to say a little bit about the capacity building work we do. LEAP is useful both as a practical planning tool, but it's also really had a lot of impact as a teaching and capacity building tool. And we've been working all around the world to help build capacity among developing countries. You can see a map over there, just some examples of places where we've done LEAP workshops in this last few years. Just in 2017 alone, we did training workshops in all these countries here. And we also work with regional centres of expertise who also do LEAP trainings themselves. So we've had a very long-standing partnership with Fundación Bariloche in Argentina, for example. This year will be their 14th annual LEAP training. So they've had a lot of impact in building up expertise in the kinds of methods used in LEAP, particularly in Latin America. We've also worked with quite a few other organizations in different regions of the world. We've also partnered with many other initiatives that are focused on building capacity for climate mitigation. The UNDP National Communication Support Programme, as it used to be called. We've worked with USAID very closely, and a number of EU-funded initiatives such as ECRAN, which was an initiative to build up climate mitigation capacity amongst countries that are applying for accession to the European Union, and a few other ones as well. And as Johan and Chris will be mentioning in a minute, we've also been working closely with CCAC to build up capacity on using LEAP for SLCP mitigation. Let's see. So the kind of our overall ambition with the capacity building is to sort of build up national mitigation commitments and build up ambition towards national mitigation commitments by building up national capacity and improving the type of analyses done in countries. And I think that's a very important area for especially international institutions to focus on going forward. It's really very striking that the level of capacity in developing countries today is really just a sliver of what it needs to be if we really want to be serious about climate mitigation. You know, there just isn't there just isn't the number and the quality of people in most countries to be able to take on the task that we are hoping they will do over the next 20, 30 years. So we really have only scratched at the surface in terms of the capacity building needs so far. So just mentioning a few applications of LEAP, at least 37 countries use LEAP to help prepare their INDCs, and many other countries are using it for their national communications, for their biennial update reports, and for low emission development strategies preparations. Some countries are using it to help prepare their NAMAs as well. A word about status and dissemination of LEAP. So this is sometimes causes confusion. So LEAP is not actually open source software, but we do make it available at no charge to non-profit academic and government institutions based in low and middle income countries. And we also make it available for free to students worldwide. We do ask everyone else to purchase a license, and the funds from the licenses go towards the ongoing development of the software, and most importantly, the free technical support that we give to everyone. So please bear that in mind if you think of using it. It is available to most countries in the world, and specifically low and middle income countries. And let me just say, energycommunity.org is the main LEAP website. That's the place where you can download the software. It's the place where you can get all the technical support, download all the training manuals, and get all the information on LEAP. So this is actually what LEAP looks like on screen. It's designed to be as standardized a piece of Windows software as we could possibly make it. You know, we've tried to make it very familiar to people who are used to using tools like spreadsheets. It uses an organizational structure there in the form of a tree. That's the main data structure where a user will organize their energy information. Typically, they'll break things down into sectors and subsectors. They may go it may break things down even further than that if they want to, but it's basically a way of sort of organizing where energy is consumed and produced and what kind of resources are available in whatever area you're studying. So typically an area will be a particular country. So that's the tree structure on the left. On the right is the data entry screen where you can put in your equations describing how much energy you're using and how that's likely to grow over time. So there, for example, you see a little equation where we're saying the number of households and how quickly they're growing over time. And you can see the results down in the bottom right-hand corner. There's other views where you look at the results and it calculates all sorts of results. It calculates energy consumption and production, emissions. It also calculates, the new IBC program will calculate impacts, and Chris and Johan will tell you more about that in a minute. And there's many other views, but maybe the one other thing to mention on this screen is this little box up here at the top right. You can see there's a place where you can select different scenarios. So LEAP is all about designing, creating and evaluating scenarios. So scenarios are stories about how the system might evolve into the future, and LEAP is sort of very strong in terms of giving you tools to examine what different pathways might look like and what the implications of those pathways might be, so that you can explore the implications in terms of energy, in terms of emissions, in terms of impacts, in terms of economic costs and benefits. Okay, this is the structure of LEAP. You can see the whole model is driven by basic assumptions about demographics and macroeconomics, so population growth, growth in GDP, structure of GDP, those kinds of things. Those drive the modeling that you do in LEAP. You always will do some basic demand analysis, so that's looking at consumption of energy. Then you will go on to think about transformation analysis. So transformation is where you think about how you're going to produce the energy needs that you have in your country. So there you'll be thinking about things like electric generation, oil refining, it could even be traditional transformation processes like charcoal making, or it could be sort of ultra modern things like hydrogen production. There's also sections where you can think about the availability of fossil and renewable resources, and there's a new module in LEAP that lets you look at land use change, forestry and bioenergy in a lot more detail based on sort of a detailed analysis of land use in the country. There's also a section where you can look at any other non-energy sector emissions. So there you can look at emissions from things like industrial processes, solid waste, fugitive emissions, those kinds of things. And then kind of hanging off, so that's kind of like the main spine of the calculations down the middle. Hanging off the sides, we have an area where we're collecting up information on all of the costs in our modeling. So if there's any cost, if there's any costs associated with the policy, whether it's capital costs, operating maintenance costs, fuel costs, externality costs, those are all collected up together and shown to you in a report that does an integrated cost benefit analysis. So you can actually study the net present value of one scenario compared to another. That's over there on the right. On the left, we have the environmental loading section. So that's collecting up all of the emissions wherever they might be happening in your model. So you might have emissions on the demand side if you're burning wood in a stove, or you're burning gasoline in a car, or you're burning natural gas in a modern cook stove. It will collect up all the emissions that come from your scenario. It will also collect up any emissions coming from your transformation analysis. So that might be, burning coal in a power plant, for example. Collects them all up and does environmental pollutant emission loading reports. So those are able to show you emissions of any kind of pollutant, whether it's greenhouse gases or local air pollutants, and it's able to show it to you in sort of tons of pollutant, or it can convert to global warming potential as well. And the new version of LEAP, IBC, also supports looking at actual sort of temperature change projections as well. Kristen Johan, again, will tell you more about that in a minute. Just want to mention a few of the studies of LEAP, just so you can get a quick sense of some of the some examples of where it's been used. You can see its history goes back a long way. I said 30 years, but it's actually more than 30 years at this point. So the very first study was a study of the Kenya fuelwood crisis back in 1984. That was a very early version of LEAP that ran on a mainframe. It's evolved a lot since then, obviously, but here's just some examples of some very early studies we did with LEAP. But you know, as early as 1992, we were doing studies of thinking about zero fossil fuel emissions. I think probably that was one of the earlier studies of that ilk. Here's a few more, slightly more recent ones, though. So this was a global study we did as part of the Rio+20 conference. So we looked at energy and emissions scenarios out to 2050, thinking about what would it take to dramatically reduce emissions and really seriously address development concerns and reduce poverty. Here's another study we did for COP15, where we looked at European Union's share of the climate challenge, looking at sort of emissions reductions for 27 EU countries, and thinking also about issues of sufficiency and equity among EU nations. So these were all studies where LEAP was used as the main sort of modeling framework and used to produce the sort of quantitative scenario results going into these reports. Here's a much more recent one we've been doing in Central and West Asia, where SEI was actually doing the modeling in support of a project run by the Asian Development Bank, looking at the costs for mitigating greenhouse gas emissions in Azerbaijan, Kazakhstan, and Uzbekistan. And this is a project where quite often we as SEI did the main modeling, but is always a very strong focus in our projects on capacity building. So a lot of that project was also about trying to build up capacity in those countries so that they can use the models themselves, and so that they can get much more involved in sort of quantitative analysis of their own energy and climate mitigation options. Here's another one that's got quite a lot of press recently. This was not one done by SEI. This was done by a coalition of groups between the US and China. So the Rocky Mountain Institute and the Lawrence Berkeley Lab, which is a US national lab, in collaboration with the Chinese Energy Research Institute, which is the leading energy research institute in China. So they were doing a study of sort of the maximum penetration of renewables and energy efficiency and what contribution that could make to China's energy roadmap for 2050. So these are all reports, and I've included the links at the bottom, and we'll share these slides later on. So if you want to explore any of these reports in more detail, you know, please follow the links that I've included on the slide. And just to mention also, if you visit the LEAP website, there's a link to it down there. There's actually more than 80 different LEAP studies listed on the website, so please feel free to visit there if you want to know more. Many of the descriptions of the projects also include links to reports and also links to LEAP datasets that can be downloaded and explored in LEAP. So just there's a quick screen. I haven't really had a chance to show you LEAP in operation, but just to give you a sense of how the software looks in action. You can produce all sorts of kinds of outputs from it: charts, tables, maps. There's even an interactive scenario explorer down here on the bottom right-hand corner that you can actually sit down with stakeholders and explore scenarios on the fly. You can actually pull these levers and see how the results change right in sort of front of your eyes in real time. So that's probably enough on LEAP. Let me just mention some things that are coming in the future, and then I'll pass it back to you, Elsa. So some things we're working on at the moment. we're upgrading the technology database that's built into LEAP. So at the moment it's rather obsolete. We're working on a new cloud-based technology and environmental database that has that will have much better default data and would also have an open API, so it can be used not just by LEAP but by any other modeling tool as well. We're working this year in particular to improve the modeling of variable renewable energy and energy storage, so it will be able to do much more detailed analysis of scenarios that include very deep penetration of wind and solar, and you really need to be able to model storage to do that. Storage and better modeling of electricity trade. We're also working on a multi-regional and urban scale version of LEAP IBC, but I'm getting ahead of myself there a bit because you haven't really learned what LEAP IBC is yet. So maybe that's a good point to stop and pass it back to Elsa and Chris, and they can tell you about this new extension to LEAP called IBC. So I'll leave it at that for now. Thanks.
Thanks, Charlie.
Thanks, Charles. Really good. I just wanted to mention I happened to be with Charlie at one of the low emission development strategy platforms a few years back, and saw you get an award, a medal for heroic work in having developed LEAP and also fully in use by the LEDS community. So just to add to the curriculum. So
the question was, if you want to build your own scenarios, can they be different from the ones that are predefined? Yes. Yeah, it's actually sort of the other way around. In fact, when you're using LEAP, there kind of aren't predefined scenarios. It's all about building your own scenarios. Yeah, so you can build any kind of scenarios you like. One of the nice things it has built into it is you can look at sort of individual policy measures on their own, and you can build up kind of a library of individual policy measures. So you might have one that's a very small thing, just like what happens if we just do kind of better brick kilns, or not. Well, it's not a small thing; it's an important thing, but it's a very specific policy. Or you might have another one that's looking specifically at electric vehicles, or another one that's looking at energy efficiency in the industrial sector. So you can look at them individually, but then you can package them together and see what the interactions are between those scenarios. So LEAP is all about sort of helping you do that, and it helps you package up scenarios and look at the interactive effects between them. And because it's an integrated model, you can see the interactions between them. So if you're doing efficiency on its own or renewables on their own, you get a different answer than if you do efficiency and renewables together, because there's interactions between them.
And just to say that we show some examples of that.
Oh, good.
Any other question before we move on, or comment? Is there anything online that you're asking? Thanks a lot, Charlie.
Okay.
Let's move over. Have a good breakfast. I think it's very early your time, no?
Yeah.
So over to Johan and Chris.
Yep.
Johan on the line and Chris in person here with us.
Hi. So can you hear me, everybody?
Very well.
That's great. So what I'm going to do is just try and take you through the analysis to support the development of national plans for short climate pollutants, and especially the link with this integrated benefits calculator. So first of all, if you take the next slide. So basically, LEAP with the integrated benefits calculator is being used to support countries who are developing national plans for action to reduce emissions, which are part of the short-lived climate pollutant story. So here we're trying to allow governments to assess, in many cases for the first time, the size of the SLCP issue, but also to develop scenarios of mitigation. And then this feeds into the national planning process, which also includes a detailed analysis of the pathways by which measures can be actually implemented. And this is all part of the Climate and Clean Air Coalition's aim to really increase the ambition to reduce emissions. But what I'm going to do now is really go back a bit in case there are some people who don't know about this SLCP framing, or short-lived climate pollutants. The next slide, please. And I'm going to talk about the origin of this framing, which was first put forward in an assessment. Next slide, please. So actually, this really came to the fore. The Stockholm Environment Institute and some partners, we organised a conference in 2008 where we wanted to look at the link between air pollution and climate change. And there was a consistent story that came out that there were a bunch of substances which were both air pollutants and affected climate, and that many of these impacts were in the near term. And a UNEP colleague, Volodymyr Demkin from DEWA, was in the audience, and then he spoke to people at one of the governing councils and then talked to me and said, well, is it a good idea to do an assessment? And we thought that this was a good idea. So, you know, we wanted to look at this issue of those pollutants which both affected climate but also had an impact as air pollutants. And these are things like black carbon, tropospheric ozone. So next slide, please. And so we got together a group of about 100 authors and undertook this UNEP WMO integrated assessment of black carbon and tropospheric ozone, which were the two substances which were both acting both as pollutants and affecting climate. And this was further developed in a sort of a more action-oriented report. And at this point, it became quite clear that developing tools was going to be quite important. And in the assessment, we undertook quite a bit of modelling. As part of the assessment, the innovation that was achieved was that we actually looked at measures. So the entry point of this is measures, and we looked at those measures which would give us a climate benefit and also reduce air pollution. And we came up with 16 measures, black carbon measures, reducing emissions, not just of black carbon, but also co-emitted substances from incomplete combustion, and also reduced methane emissions. And this all led to was fed into some global modeling, which allowed us to look at the impact of this on temperature. So in the next slide, please. And this is quite a famous graph, at least in the circles of the CCAC. And this shows that, you know, if you take the historical record in black, and then you get the purple line at the top, which is the reference, and this is the change in temperature anticipated over time, that, of course, mitigating CO2 is very important and will lead to a reduction in warming over the long term. But that there was a bunch of measures which were addressing black carbon and methane emissions, which could actually reduce the temperature over the next few decades, and that ideally we'd be doing both at the same time, and then we could lead to a better pathway towards the future warming that will occur. And this raised a lot of interest, but not just because of the climate story, but in the next slide, we know that PM 2.5 is one of the main causes of human health impacts, and many of the sources of PM 2.5 were emitted by the measures we were looking at in terms of this black carbon and tropospheric ozone story. So next slide, please. And we calculated as well, using the modeling approaches, that we could save over 1 million or 2 million lives per year by implementing these measures, particularly those related to incomplete combustion. And there were some countries where there are large air pollution impacts which would be set to benefit hugely from this. But it's not just about air pollution impacts on health, but the next slide. We know that tropospheric ozone is a big cause of the reduction of yield of some key crops such as maize, wheat, soybean, rice. These are all experimental data which shows that the current levels of ozone are reducing crop yields by up to 15% or so. And so we also looked at this, and by implementing all the measures, we could reduce ozone as well, because methane is an ozone precursor, and the incomplete combustion also emits precursors of ozone, and so by taking action, you reduce the impact of ozone, both on crops, as this is the results for crops, but also on human health. Next slide, please. So basically, we had then a story of substantial health benefits, and we didn't even calculate the indoor air pollution deaths that would be reduced from the action, especially considering that the reduction of emissions from cooking with fuel wood was included as one of the measures. So we also have the energy benefits, because if we have increased efficiency, we reduce the energy requirements. We have agricultural benefits, which can have an impact on food security, and then the climate benefits, which can halve if all of those measures, 16 measures, were implemented, they can halve the amount of warming over the next few years. So if we take the next slide, please. So what we did then was to look at the what would we need to support countries. And so we'd been working on air pollution a lot here in the York Centre of SEI, and Charlie had been working on LEAP for many years, and every time we met for quite a long time, we said we really should collaborate, and here was the perfect opportunity. And we saw that there was a need to have a planning tool to really put together the information, because we saw how important it was to be able to show the quantitative data in the global assessment, but that countries needed to have the same level of data. So what we've done is, on top of the LEAP analysis, which you saw, we've enhanced the emission estimation for those pollutants which are important for PM2.5, for tropospheric ozone, and affect climate. But then, of course, pollution is a local and regional phenomenon, and so we've linked the emission estimation from LEAP with the results of atmospheric transfer models to estimate concentrations, and from this we can assess health benefits, we can assess climate benefits and crop yield benefits. And this is what we've put together in this so-called integrated benefits calculator. So next slide, please. So if this is just a brief overview of what you would need to do if you were a country wanting to implement the LEAP with the integrated benefits calculator. First, you would need to assess all of the energy and non-energy sources of emissions, and you also need the drivers of the scenarios, particularly things like population growth and GDP data for the country or different sectors, and then you build a number of scenarios. So the next slide. And then we calculate the emissions. So as I mentioned, we calculate all of the emissions which give rise to PM2.5. So this would be black carbon, organic carbon, nitrogen oxides, sulfur oxides, ammonia, but also those precursors of tropospheric ozone. So you've got carbon monoxide, the non-methane volatile organic compounds, as well as methane. But we also have the existing CO2 and other greenhouse gas emissions as well. So then we need to grid these emissions, because we need to know where they are in the country, and then we create emission scenarios by linking the development of each sector with the key drivers. So the next step. We then use the result of an atmospheric model. So we collaborate both with the US EPA and through them with Davin Henze at the University of Colorado. And he runs a global atmospheric transfer model and chemistry model called GeosChem. And he gives us some coefficients which link the emission to the concentrations, and we can estimate the concentrations of PM2.5, which causes the largest health impact, as well as ozone. But we also can take the emissions and estimate radiative forcing. And then the next slide. Now this is just emphasizing what we do with the GeosChem adjoint model. So we have these coefficients for every country, and if we multiply the emissions from a country times the coefficients from for the grid where the emission is made, we can estimate the concentration of nitrate, ammonium, sulfate, all the components of PM2.5, and we add them together to give us an estimate of what the total PM2.5 is in a country. And then we can estimate scenarios. So then LEAP IBC automatically calculates health impacts, crop impacts, and climate impacts. So we take the PM2.5 data and we have information on different impacts, and we can estimate the number of premature deaths which are caused, or which the benefits of reducing those deaths by taking action, as well as the number of tons of crop yield, and estimate the climate impacts in terms of the temperature change in annual time steps. So the next slide, please. These are the dose-response relationships which come from the global epidemiological literature, and we have these different impacts of PM2.5 on strokes, heart disease, respiratory infections, lung cancer, and from this we can estimate the causes of death, or the death which is caused from these different causes from different PM2.5 concentrations. So the next slide, please. And the same with, we can estimate the crop yield reductions from ozone. So, and in terms of the climate impacts, so Drew Shindell was the chair of the UNEP WMO assessment, and he developed the methods which allowed us to estimate from the emissions and the location of those emissions what the impact would be on the temperature change in different latitudinal bands. And these are then output in annual time steps by LEAP IBC. And the next slide. So I think this is out of date now. Chris, I think you know how many countries we have, but Davin Henze has to run his geochem model for every country for PM2.5 and ozone, and this is a map of where we were in December last year in terms of the number of countries where we had coefficients which will allow us to estimate the concentrations and impacts. So with that, I'll finish.
Thank you very much, Johan. And in this case, we are gonna turn over.
Elsa, can I just add one quick thought?
Yes, of course.
Charlie. Well, one thing I think it may be that Johan didn't mention is that part of the contribution of putting all this stuff together in this one package is that we've sort of taken these very sophisticated methods that have been done before by very large institutions, but there's something that can only be done by those large institutions. They require a huge amount of computing power. Doing a run for a country for ozone, for example, using the geochem model takes many days to do that calculation. But what the team in New York and others have done is to package it all up and parameterize it and put it into a package that's now on a fairly simple Windows-based modeling tool. And now you can do that kind of modeling in a matter of seconds now. So it's something that's become practical for developing countries to do themselves. I think that's sort of the key take home here, is sort of taking something that was the domain only of large institutions and making it available for developing country institutions.
And I think that's probably quite a good introduction to what I'm now going to talk about, which is how we've been applying this LEAP IBC tool as part of the CCAC SNAP initiative in 12 different countries so far, and how they've been able to use these methods to actually enhance their analysis of the benefits of different SLCP, air pollution and climate mitigation strategies. So I'm going to focus on two examples, mainly focused on the work that's been done in Ghana over the last couple of years, and also present some results for work that's ongoing in Chile. So in Ghana, they produced their first national SLCP plan in 2013. They were one of the founding countries of the CCAC and one of the first countries to produce a national SLCP plan, which contains some measures that they wanted to look at. But since then, there's been a lot of work in Ghana on various different policies and measures which relate to agriculture, forestry and land use, which relate to renewable energy and energy efficiency, relating to climate change policy, air quality and sustainable development, that have all been put together and potentially have implications for SLCP emissions. So the aim in doing the LEAP IBC analysis as part of this second phase of the CCAC SNAP initiative was to actually evaluate all these different policies that are in place in Ghana, to see what the estimates of the emission reductions are and what implications they have for human health, for crop and for climate of implementing these measures, with a view to increasing the ambition of the implementation of these measures because of the multiple benefits that could accrue from them. And I should say that the work that I'm going to present and the methodologies that have been used have been led by the Ghana Environmental Protection Agency and specifically our colleague there, Daniel Benefo. So this SEI and the CCAC have supported this analysis, but it's been undertaken by Daniel at the Ghana EPA. So the first thing that Daniel did in developing his LEAP IBC analysis was to enter in activity data for all the major energy and non-energy source sectors. So the left-hand screen here shows an example for the residential sector where he's entered in data in a lot of detail. And one of the features of LEAP, it doesn't have a fixed data structure. You can change how you represent emissions from different source sectors depending on the amount of information you have available and what type of analysis you want to do. So nothing is fixed in terms of how you represent the residential sector. And the way that the Ghana EPA approached this data analysis was to set up the LEAP data set in a way that they could directly take data from existing reports that are regularly collected. So the Ghanaian government do a living standards survey every 4 or 5 years, and they set up their LEAP data sets for the residential sector so that it was split into Accra and other urban areas and then split into the 3 different rural areas, so they can take the information that's produced in that data set and put it straight into LEAP in a very easy way. So one of the advantages of this is that as things change and new data becomes available, it's very easy to then update their LEAP IBC analysis. And one very nice example of this is that the 5th round of the Ghana Living Standards Survey took place in 2006. And in terms of what fuels people were using for lighting, in 2006, about 50% of the Ghanaian population were using kerosene. They did the 6th Ghana Living Standards Survey in 2013, and that had dropped to 3.6% because of electrification in rural areas. So Daniel, because it was set up in a consistent way with these surveys, was able to simply change this data, which then reflects the more current situation very easily. So having entered all that data for an emission scenario for a base year, it was then the Ghana EPA's task of developing a baseline scenario as to how things were going to change into the future. And as Charlie mentioned earlier, this is about developing stories about how things are going to change for each of the data points that you're looking at. So, for example, the Ghana EPA estimated the urbanization rate. So this LEAP screenshot here shows the proportion of people living in rural areas in red and the urban areas in green over time. And this trend towards a larger urban population is based on Ghana's expected change in population and a decrease in household size, and combining that together gives you a 2.8% increase in the number of households with a increasing share of them being in urban areas. They also wanted to look at to reflect in that baseline scenario, the different policies and measures or PAMs that the Ghana government had already committed to. For example, the further electrification of different rural communities. But they also wanted to see what the benefits of actually achieving those things are, because some of these policy measures are ongoing and implementation is going into the future. So they set up, in effect, 2 baseline scenarios where the policies and measures were successfully implemented. And the graphs on the left-hand side here, the top one shows the number of electrified households in rural savanna areas in Ghana. And you can see that by 2025, there's 95% of households in rural savannas areas in Ghana have electricity, whereas the estimated the failure of that policy and measure means that it takes much longer in order for those communities to have electrification. And both of these situations can be reflected in Ghana's LEAP IBC analysis. In terms of, so once they had set up the baseline, it was then their task to identify what mitigation measures they wanted to evaluate using LEAP IBC. And as Charlie said in response to your question, there's no default scenarios within there, so it was up to them to determine what the scenarios were they wanted to look at. So they set up 5 different criteria through stakeholder engagement within Ghana to identify what mitigation measures they wanted to look at. So the contribution to the SDGs, how aligned the SLC, the short-lived climate pollutant mitigation measures were with other national and sectoral priorities and with their NDCs, the actual how much the measures could reduce SLCP emissions, how long they would take to be implemented, whether they were feasible, and how much they would cost. And once they had done that analysis, they came up with about 15 measures that related to lots of different sectors that had the potential to reduce short-lived climate pollutants. They included clean cooking, renewable energy, transport measures, agricultural measures, a whole range of things that could be implemented. And then it was their task to decide, having determined what the measures were, to model them in LEAP, to say what that means in terms of changes in the activity in different sectors. So this is an example for their clean cooking scenario, where the target is to have 50% of households in 2020 using LPG. So you can see in the current policy and measures failure, you've got a much larger number of people cooking using wood stoves compared to the graph below, where you have a much greater penetration of LPG. And then you can look at the implications of this for different emission reductions. And then, as Charlie was saying earlier, the Ghana EPA then grouped these different measures into different packages of measures. So you had the measures which they called the low-hanging fruits, the measures that were most technically feasible and had the highest commitment from governments, and that was the renewable energy, setting up solar systems and having LPG for cooking. These have large buy-in from government already, so they were the 2 highest priority measures. They then had a set of measures called Additional Policy and Measures Plus, which were the rest of the measures that had been specified within their NDC. And then, having evaluated those NDC measures, they came up with 4 more that were specific to targeting greater reductions of short-lived climate pollutants. So additional action on transport, on agriculture, and some specific industries, and that was called the Additional Policies and Measures Plus. So within LEAP IBC, they were then able to look at what the results of these different packages of measures were in terms of their reduction of black carbon and methane, but also other emission sources as well. So you can see that for the failure of current policies and measures, you have an increase in black carbon emissions from 2010 to 2040, and then a progressive reduction in your black carbon emissions relative to that failure for successfully implementing current policies and measures, for additional policies and measures, and then finally implementing everything that that in the analysis gives you the greatest reduction. For methane emissions, the story is slightly different. For the methane emissions, the failure of current policies and measures and the success of current policies and measures and the additional low-hanging fruit actions don't have that much effect on methane emissions. They're not specifically targeting methane. It's only when you get to implementing all of the NDC commitments that you get the largest reduction in your methane emissions. So there's the different actions within your groups of measures that are having your largest effect on methane emissions. And as Johan was saying, in LEAP IBC, you can now go as far as looking at impacts. So you can translate all of those changes in emissions into the effect of Ghanaian emissions on global average temperature change. So the scale on the left-hand side looks very small in terms of degrees C, but you can see that from implementing the NDC actions, the additional policies and measures, and the SLCP policies, you can reduce Ghana's contribution to climate change by about 50% relative to the failure of current policies and measures. And with the atmospheric modeling that we have from Davin Henze at the University of Colorado, we can also look at the implications of those same measures on air pollution impacts. So this graph here shows the number of premature deaths associated with exposure to ozone and exposure to particulate matter in Ghana from 2010 to 2040 under the PAMS plus scenario. And what you can see from this is that it's split into the contribution from Ghanaian emissions in yellow, from natural background in green, and from rest of the world emissions in blue. So you can see that the ability of Ghana to actually reduce air pollution impacts from reducing emissions in Ghana is relatively limited, because you have a relatively large contribution from the natural background, and that's the Saharan dust that comes down in sort of March to May time with the Harmattan winds, results in very high natural PM 2.5 concentrations. And you also have neighboring countries that are with emission sources that are contributing to air pollution impacts in Ghana. So the avoided deaths from implementing the measures within Ghana's national SLCP plan are relatively small when you look at the total. But if you compare it to the yellow fraction, which is just what the contribution from Ghanaian emissions, actually taking these measures can reduce the air pollution impacts from Ghanaian emissions by about 30%. So it's doing a relatively significant reduction in terms of what they can actually control and what they can reduce. So having done that analysis and provided a story as to what these measures can do in terms of reducing emissions, the intention and what they're doing is developing the national SLCP plan, so the next phase of their national SLCP plan. And this provides, the LEAP IBC analysis provides the quantitative numbers that can be used to justify taking action on SLCPs. And the next step is for them to then take each of these measures and develop concrete actions that can lead to the implementation of these measures that can then be monitored and evaluated over time. So, for example, one of the measures is to look at the implementation of soot-free buses in Ghana. So Ghana EPA have determined the steps that need to be taken to do that in terms of getting a commitment from the Transport Ministry to implement soot-free buses, which has already been secured. But then they've also thought about the different organizations that need to be involved in setting emission standards for vehicles, which is the Ghana EPA and the Standards Board, and then the different organizations that need to be involved in enforcing those standards at the ports, on the road, and on the road. They've developed a plan as to what investment in infrastructure development needs to take place. The Ghana Gas Company to supply the natural gas for the buses, and working together with private sectors and local authorities in order to actually get buses running on the road. And they have the level to which each of these actions and each of these steps have been taken and what additional actions need to be taken, so that they can really chart that link between what the benefits could be and how it could be implemented on the ground. The other place where these results from LEAP IBC are being used in Ghana is in their in what they call their Ghana Climate Change Data Hub. So this is a repository of a large amount of information related to climate change from Ghana. So this is where they show to the public the extent to which they have, for example, implemented the different NDC actions. So it comes with information on what those NDC actions are, how it's going to work, but it also has a space for co-benefits. So they have some information on what the co-benefits are, but the LEAP IBC analysis can also feed into that as well. So I think the final thing I want to do is just to show you a quick example of how LEAP IBC can be used as a communication tool. So we're working with the National Technological University in Chile and the Ministry of Environment to develop a LEAP IBC analysis to assess the air quality co-benefits of their climate change plans and vice versa, the climate co-benefits of their air quality plans. And in a month or so ago, the Ministry of Environment and the National University presented their LEAP IBC analysis to the Ministry of Environment in their last meeting with them. So if I press escape, do I get to LEAP? So this is what LEAP looks like. And the interest that they have, the two particular measures that they're interested in implementing is electric mobility. So they want to see what the implications of switching to electric vehicles are, and they're also interested in looking at the benefits of reducing emissions from heating stoves in Chile, particularly in rural areas. So they have developed a LEAP IBC analysis that contains this particular example contains the transport sector split by different types of vehicles, urban and interurban travel. But in communicating these results to the Ministry of Environment, they used a feature of LEAP called the overview screen, which Charlie touched on earlier, that lets you look at the extent and the speed of implementation of different measures and what it means in terms of emission reductions or impact. So the example they used here were for putting in electric buses and electric light-duty vehicles. And using these sliders up here, you can determine the year in which electric buses come in, whether it's very soon or whether it takes longer to implement, and the percentage change in the number of vehicles that are electric buses. And you can do the same for light-duty vehicles as well. And what you can see with this current situation, we have electric buses being implemented by about 2030, fully implemented, and for the CO2 emissions, but emissions of black carbon or NOx or other pollutants from transport, you have this decrease in terms of CO2 emissions from the transport sector, which is good. But when we look at the emissions from electricity generation of CO2, we have this disbenefit. So in just doing the electric bus scenario, with the current fuel mix for generating electricity, gives us a benefit in terms of reducing CO2 from tailpipe emissions, but it has a disbenefit because there's more electricity demand and therefore more CO2 emissions. So in showing this to the Ministry of Environment, they were able to look at the extent to which there would need to be penetration of solar energy to offset this disbenefit. So if you change the percentage of solar energy production in Chile and then refresh the scenario, it will very quickly tell you what the effect of that is. So having more solar can maybe take away that disbenefit. So if you change the proportion of your electricity generated from solar to 35% rather than 30%, you still get the benefit in terms of reducing tailpipe emissions of CO2 from transport, but then you're also getting a benefit in terms of reducing your CO2 emissions from electricity generation. So I think that was my final slide, or maybe there's just a couple of things to say. How do I make it? Yes, so they were the two examples that I wanted to talk about. We have some future changes that we would like to make to LEAP IBC in terms of visualization of results. So it'd be great to show the gridding of LEAP emissions, and as Johan described, we're looking to try and categorize the multiple benefits that could result from these scenarios, so including more health effects of air pollutants, including additional crops in terms of the vegetation impact, adding in information on costs, and then the final thing on that list is the urban application. So at the moment, we just apply LEAP IBC at the national scale to get country level results, but we're in the process of developing a version that can be applied at the urban scale. And the first application will be in Accra in Ghana, and then in Nairobi in Kenya, where you'll be able to look at what the contribution to air pollution in Accra, for example, would be from international sources, from sources within the rest of Ghana, and then sources local to Accra. So you can get more specific as to where action is needed to try and reduce PM 2.5 concentrations within Accra. Yeah, thank you very much.
Okay.